So this is lecture 2 in unit 2. Energy momentum is the unit, and the lecture is kinetic energy and work. It's section 4.2 from your textbook, and we'll learn about the work-energy theorem in this lecture. So you might recall from last year that a moving object has the ability to do work, and this is because it possesses a type of energy we call kinetic energy. So if we have a hammer, due to its kinetic energy, it can hit a nail and transfer its energy to that nail and do work by moving that nail a certain distance into a board, for example. The faster the hammer, or the more massive the hammer, the greater its kinetic energy. So the greater the displacement of the nail. This is what you need to copy down. It's the kinetic energy equation, and it's EK equals 1/2 mv squared. Kinetic energy, and all energy is measured in joules, and it's the kinetic energy is the energy possessed by a moving object. So looking at this little practice question, this is just to understand it a little bit. Let's say we double the speed of a car. What happens to its energy? Well, assuming the speed was 10 meters per second, and if we found the kinetic energy of that, that would be 10 times 10, or 10 squared, which is 100. If we double that 10, make it 20, then we have 20 times 20, we have 400. So because it's a square relationship, when we increase the factor, we actually increase the kinetic energy by a square of the factor. This is, as a proportionality, this is the kinetic energy is proportional to the square of the velocity. So for example, I'll just switch over to 26% increase. So if we increase the car's factor by the velocity by 1.26 and we square that, we end up with about a 1.6 increase in its kinetic energy. So we have a situation here. We have a cart that's moving with an initial speed of vi, and it experiences a force that causes its speed to increase to vf over displacement d. Using this situation, and we know that work equals force times displacement. We know that force equals mass times acceleration. We also know that vf squared equals vi squared plus 2ad. We can rearrange this into what's called the work-energy theorem. This is that the work is equal to mvf squared over 2 minus mvi squared over 2, or the work is equal to the change in the energy, the kinetic energy in the final position from the initial position. It gives us the work done. So that's our work-energy theorem. And just to show you, actually, I'll show you the example on the next slide. But it says here you can use the work-energy theorem to solve several types of physics problems. However, the theorem is only true if no energy losses occur. In many real situations, energy will seem to disappear in the form of light, sound, heat, or changes in shape of an object. For example, in a car collision, energy goes into the sound of the crash and the bending of the materials in the car. So in this case, the work done on the car does not equal the change in the kinetic energy of the car. So because the work-energy theorem has to incorporate every sort of change of energy, it seems like it's not that useful, although we can use it in specific situations. We'll get into that a little bit later. So what I'd like you to copy down is the work-energy theorem slide here. It's only true if no energy losses occur, and energy losses could be in the type of sound or heat or deformation. The subscript I and f are our initial and final. The main way of kind of thinking of this is just the work equals the change in the kinetic energy from the final to the initial position, or from the initial position to the final position. So here's a situation. We have a whale. It has a mass of 15,000 kilograms, and it's swimming with a speed of 6.1 meters per second. And then it hears a sound that startles it from a boat, and it increases its speed to 12.8 meters per second. So the change in energy is what we're interested in. So this is the whale's mass times 1/2 times the change in the squares of the velocities. So 6.1, rather, sorry, 12.8, its final velocity squared, minus 6.1 squared is 949,725. We round to 2 significant digits, and this becomes 9.5 times 10 to the 5. We'll look at another type of problem here. Let me switch. So this one says the police car has a mass of 2.4 times 10 to the 3 kilograms. It's traveling on the highway. It receives a call. It increases its speed to 33 meters per second. And there was 3.1 times 10 to the 5 joules of work done. So we have to figure out what was the change in the, or we have to figure out what the original velocity it was traveling at is. So we're interested in, our work equals EKF minus EKI. Our work also can be written as 1/2 mvf squared minus vi squared. We're solving for vi. So I'm going to rearrange this for vi. So this becomes, the 2 moves over here, so this is 2w. We divide by the m. We move the vi over to this side. We have to square root everything. So this becomes vf squared minus 2w over m. So vi equals the square root of 33 squared minus 2 times, don't have the number right here, let me just write down this one, 2400 is the mass. I'm just going to click back here. It looks like it's 31000 to the 5. So putting this into our calculator, we end up with 33 squared minus 2 times 31124 divided by 2400, close the bracket, and then we find the square root of this. We end up with a VI of, reporting for, how many significant digits do we have? Well, we have to write this in, there's really 2 significant digits, but it looks like we'll lose too much information in that case. So I'm going to write this down as 2.8 meters per second. To change that into kilometers, it's 28.8 meters for every second. And then what I need to do is I need to change those meters into kilometers, so I need to divide by 1,000. Look back at my calculator. Divide by 1,000. Then I need to multiply by the amount of seconds in an hour, which is 3,600. So this is 3600 seconds per hour. And this is 1,000 meters per kilometer. What we end up with is, after rounding, 104. This seconds in the numerator divides by this seconds in the denominator. This meter in the numerator divides by this meter in the denominator. This per kilometers in the denominator ends up going to the numerator, and this per hour in the numerator ends up going into the denominator. So those are our, that's our solution for this problem. Let me go back over here and switch to another question we have here. We have an archer who pulls back a bowstring. It's loaded with an arrow that is 22 grams. They release the string. and the arrow leaves with a speed of 220 kilometers per hour. So let's start this off with a, we need to find our work. So our work equals 1/2 m v2 squared minus v1 squared. I kind of switch between the i's and the 2's, i's and f's and 1's and 2's, just to show you that it doesn't matter what you use. Now in this case, this arrow was not moving initially, so this whole term becomes 0. We need to solve for w, so our equation is already arranged. So this is just 1/2 m v2 squared. 1/2 of m, which in this case is 0.022, v2 squared. So what I'm going to do for this one is, it's 220 kilometers per hour. I have to multiply that 220 by the amount of seconds. Sorry, no, let's do this the other way around. By the, I have to change the kilometers to meters by multiplying by 1,000. And I have to divide by the number of seconds in an hour. So this is what I'm going to be entering in, my calculation. So because this is squared, I'm going to start with the squared term. So 220 times 1,000 divided by 3,600. That term is squared, times 0.022 divided by 2. That gets me to a work of 41 joules. Last problem we'll do. We have two objects that have the same kinetic energy. One has a speed that is 2.5 times the other. So determine the ratio of their masses. So it says that they have the same kinetic energy. So in this case, let me just go back here so I can see. If they have the same kinetic energy, then that means that their 1/2 m1 v squared has to equal 1/2 m2 2.5 v squared. The 1/2 here and the 1/2 here and the they would divide out. To find the ratio of their masses, what I need to do is I need to find out what's m1 divided by m2. Or to find m2 divided by m1. This v squared will divide by that v squared. So I'm really just left with what's the square of 2.5. And that's going to be 6.25. So the ratio of their masses is 6.25. One is 6.25 times larger than the other. And that's it for this lecture. Make sure you do the homework, and if you have questions, please let me know.